we construct our 2D Mohs circle. Okay, so with our 2D Mohs circle, the information that we need to calculate. So what are the things that we need to know? Okay, so the first thing we have to determine now is our stress average. So we have to determine our stress average. So the stress average is the distance from here to here. Okay, so this is our stress average. Okay, so the formula to determine our stress average is very straightforward. Okay, so stress average. So we are going to determine the center of the circle. And determine which we usually have a dot down here. We call that point O. Okay, so we're going to determine center of circle. Which is for this case our stress average. So this is equal to stress X plus by stress Y divided by 2, right? And then I'm going to connote that stress Y is equal to 0. So therefore, the stress average is equal to stress X divided by 2. And if you look at normal stress X, right, is equal to my over Iyy z, right, minus mz over Izzzy. Okay, so what I'm trying to elaborate down here, that this is due to bending moment. Okay, this is due to bending moment. So what we tend to do is we also want to call this stress small m. Okay, so m over here is a stress induced due to bending moment. Okay, I circle the word m down here. Let me write properly. I will highlight the m down here because the m down here is related to this m down here. Okay. So therefore, what we have is stress average is equal to stress m divided by 2. Okay, and I'm going to connote no axial force for these cell formulas. Okay, you cannot have axial force at all. Now, in terms of shaft design, right, if we look at our Mohs circle, we have to determine our tau max. And we have to determine the tau max. And I'll tell you all why very soon. Okay, so we have to determine our tau max. So this over here is our tau max. Okay, and to determine the tau max, the formula again is really straightforward, and you guys are really good at it now. Is the radius of the circle. so which is your tau max, and this is equal to your average stress plus by the shear stress in the xy direction square. Okay. So why is it important to know the tau max? Right? Why? Okay, why is so critical to know the tau max? So if we were to construct, okay, the operating boundary now, okay, so I'm going to sketch the operating boundary, okay, or superimpose the operating boundary due to the material property. Okay, so this is the operating boundary. So 2, 4, 6. Okay, so this is the, okay, so hold on, 2, 2, 4, 6, 8, 10, 12. So this is our operating boundary. And again, hold on. And I went over, okay, deliberate, not intentionally, okay, it's intentional. My bad, I should have drawn my text better. Now, why this limit over here, right? Why this size of the red box? Because this value over here, okay, is the shear stress allowable. Okay, and it can be your shear yield, right? And this is from, this value is from material testing. Okay, it's not calculated. These are from material testing. Okay, and what we have down here, this point over here, is our shear stress or normal stress allowable. Okay, which is your normal stress yield, right? And this is also from material testing. Okay, so this uh, circle, as you all know, we've done this last lecture, cannot be bigger than this rectangular red box, right? It cannot be in the shaded region. That is why I have to teach 3D mold circle first, then I can teach your shaft design. Okay, you all now understand this. Okay, because some of you might think, hey, Eugene, you just tell us that we only need 2D mold circle for this. Why do you learn 3D? Why? Because we have to construct 3D mold circle in the shaft design, so we realize that 2D is sufficient because of the stress state. Okay, we can only know that if you know the construct 3D mold circle. Then we superimpose mechanical properties, which the lecture we done last on Tuesday of week 11. So we realize that the yield strength, right, is half. Sorry, the shear yield, right, is half of the normal stress yield. Okay, that's why you count my boxes on the vertical. There are 6 boxes on the horizontal. I have to draw 12 for that reason. Okay. So what we realize that we know now, right? Due to this relationship, right? Due to this relationship, right? That we know that the stress yield, right, is equal to twice the shear in yield. Okay. So this value down here is the smaller value. right? That value over there, right? This value over here is a smaller value. So therefore, in order to design the shaft, okay, so for shaft design, right, we must ensure that the shear yield, right, is less than the maximum allowable stress. Okay, or the maximum, or sorry, what am I? The yield stress or the maximum stress must be smaller than the yield stress. So this yield stress over here is from material testing. The tau max over here is from structure analysis. Okay? It's from structure analysis. Okay, and this formula is on it, or the above relationship is only valid for ductile material. When I say relationship, is this relationship over here and this relationship over here. Okay, it's only valid for ductile material. We cannot use this for brittle material at all, unfortunately. Okay, it's only valid for ductile. So we realize that these cell formulas that we are deriving is A, it has zero axial stress. B, shear force are very small. C is only valid for ductile material. You cannot use this for brittle material. So now coming back to this equation, okay, that we have the relationship where tau max is equal to the square root of stress average squared plus by shear xy squared. So this is the most important. This we have to determine tau max, then we have to apply this relationship. Okay. So we also know that tau max is equal to stress due to bending moment squared plus by the shear xy squared. Okay. So stress M we derived earlier. This is where we have our stress M. Okay. Then from here, we are going to going to write down a relationship for stress M. Right. So we know that stress M is equal to the moment for Y over I Z squared plus. I'm going to put it plus down here. Okay, I'm not going to do the minus sign. Okay, I'm going to add them because when you, sorry, later on when we square them, it does not really matter. Okay, so this is mz over I z z y, right? And then the shear xy is equal to what? Is equal to tx, right? The torque in the x-axis, radius over j. Now j, there's no j x-axis of j y over here because it's a shaft. J is the second polar moment of area.